You know when you go on a site like Amazon, you type in something super specific like good battery phone under $500 and boom, you get thousands of perfect results like instantly? It seriously feels like magic. But behind the scenes, it's not magic at all. It's just some brilliant engineering. So today, we're going to pull back that curtain and see exactly how it all works.
Right, so this is the big question, isn't it? How on earth can a system dig through millions or, hey, even billions of documents, product reviews, articles, you name it, and give you precisely what you're looking for in less time than it takes to blink? It's a huge technical challenge, but the solution, well, it's just incredibly clever.
Okay, so to really get why Elasticsearch is such a game changer, you first have to understand what it's replacing. If you tried to do this on a classic database with a standard SQL query, yeah, it would work for a little while. But as your data grew, it would just crawl to a halt. And that's because those databases were never ever designed for this kind of massive text search. They're amazing for other things, but not this. Elasticsearch, though, it was built from the ground up for this one specific, difficult problem. At its heart, Elasticsearch is what we call a distributed system. Now, don't let that term throw you. All it really means is instead of putting all your data on one single, gigantic, super expensive computer, you spread the work out across a whole group of normal machines. We call these individual machines nodes, and when they all work together as a team, we call that a cluster. This idea is the first key to its incredible ability to scale.
So inside this cluster, our data gets organized into something called an index. You can pretty much just think of an index like a database in the old world. It's just a collection of related stuff, like all of our product reviews. But here's the really clever part. The index gets broken down into smaller, self-contained pieces called shards. Each shard is like its own tiny search engine. And by splitting the big problem into lots of small problems, we can have many machines working on a search all at the same time.
Let's make this way more concrete. To really see how this works, we're going to follow a single piece of data on its journey. So imagine a user leaves this review on our website. Battery life is amazing, but camera is average. What actually happens to this sentence the second they hit that submit button?
Well, the very first place that review lands is a specific node in the cluster called the coordinating node. Its job sounds simple, but it's absolutely crucial. It acts like a smart traffic cop. It looks at this new review, and its only job is to figure out exactly which shard is supposed to store it. Once it knows, it just forwards it to the right place.
Now, before that review gets saved, something really important happens. It goes through what's called a text analysis pipeline. See, Elasticsearch doesn't just store the raw sentence. First up is tokenization. It breaks the sentence into individual words, or tokens. Then, it makes everything lowercase, so a search for battery also finds battery. And finally, it gets rid of common stop words like is, but, and the, because they don't really add much meaning to a search.
And what we're left with is this, a nice, clean list of the words that actually matter. Our original sentence has been totally transformed. And this list is what the system is actually going to index. This isn't just about saving a little bit of space, it's about making the data perfectly structured for super fast searching down the line.
And this right here, this is the secret sauce. This is the whole game. It's called the inverted index. See, a normal database would map a document ID to the words inside it. Elasticsearch flips that completely on its head. It creates a map from every single unique word to a list of all the documents that contain that word. So, when we search for battery, the system doesn't have to scan every review. It just looks up battery in this index and instantly gets a list of all the matching documents. It's unbelievably fast. All right, so we've seen how data gets in, but what about getting it out? A totally new user shows up and they type good battery into the search bar. How does Elasticsearch use everything we've just set up to find those results in a flash? The search process is just as efficient. The request first hits a coordinating node. But this time, instead of sending it to one place, the node blasts the search query out to all the relevant shards at the exact same time. And that right there, doing it all in parallel, is a massive reason why it's so fast. Each of those shards uses its own local inverted index to do that instant lookup we talked about. They all find their top matches, send them back to the coordinating node, which then gathers everything up into one final, neat list for the user.
But you know, just finding documents that match isn't enough. We need to show the best, most relevant result at the top. To do that, Elasticsearch uses a clever scoring algorithm, usually one called BM25. It's basically a math formula that calculates a relevant score. It gives more points to documents where the search term shows up a lot, or if the search term is a rare and important word overall. It's all about relevance.
So we've got incredible speed, and we've got smart relevance. But what happens when things go wrong? I mean, we're relying on a bunch of different machines, and in the real world, hardware fails. A server can just die. So what happens then? Does everything just break?
Nope, not at all. And the reason is something called replication. For every single primary shard of data we have, Elasticsearch automatically makes one or more copies, which we call replica shards. And here's the genius part. It's smart enough to always place a replica on a different machine from its primary. So if primary shard 1 is on node 1, its replica will be on node 2 or 3. This simple strategy means there's no single point of failure.
Okay, so let's see it in action. Bam! Suddenly, node 2 just goes offline. The power cord got kicked, out, whatever. It's gone. We've just lost a primary shard and a replica shard that were living on that machine. In a lot of other systems, this would be a total disaster. So, what happens now?
And this is where the magic of resilience really kicks in. The system immediately detects that node 2 is gone. It sees that primary shard 2 is missing, but it knows there's a replica of it safe and sound on another node. So it instantly promotes that replica to become the new primary. Just like that, the system is back to being 100% operational. Zero data loss, basically no downtime. Then, to be safe, it automatically creates a new replica on another machine to make sure we're protected again. It's all completely self-healing.
So let's just boil it all down. Why is this thing so fast? First, the inverted index gives us those instant lookups. Second, sharding lets us search across many machines in parallel. Third, replication not only gives us safety, but also helps spread out the search workload. And on top of all that, the system is really aggressive about caching results, so if people search for the same thing over and over, it's even faster.
And of course, in the real world, engineers push this even further. They use things like bulk indexing, writing thousands of documents at once to get way better performance. They also set up hot and warm nodes, which means they use really fast, expensive storage for new data that gets searched all the time, and cheaper, slower storage for old data that's rarely accessed. It's all about balancing performance and cost.
So there you have it. The next time you type something into a search box and the results come back in a snap, you'll know it's not actually magic. It's this beautiful, intricate dance of distributed system principles all working together perfectly. And it kind of makes you wonder, right? What other complex things that we use every single day are powered by this kind of hidden, brilliant engineering?